Hey everybody, this is Mrs. Dinkelman, and these are the last set of notes for the year about polar area. I'm going to skip that first page. Really, that's for if we were actually together and in groups and we could kind of work on this. But what it's trying to get us to understand is the way that we collect area for polar. So first of all, back to some geometry. So the area of a sector of a circle is 1/2 r squared theta, where theta is in radian. So first I want you to notice that over here in our formula. Okay, so the 1/2, the r squared, and the d theta. And that's because when we're thinking about area, we're going to be thinking in kind of a circular motion. So if we start here, we're going to be thinking about what happens if we go that way. So again, think about radar as we go around the circle in that way instead of like left to right or top to bottom. Well, really what we do here is instead of Riemann sums, what we have is a bunch of little sectors of circles, so little pieces of pie or pizza. Okay? And if we have an infinite amount of those, then the theta is really 0. The angle between making the sector would be 0. Okay? So that's kind of the way we need to think about the area. So in example 1, it's just a matter of having the formula memorized. Now I'm going to hesitate a little bit about this 0 to 2 pi. We're going to talk about that here in a second. So 7 plus 6 cosine squared d theta. So again, 1/2 r squared d theta. And the reason I was hesitating is because we can't always assume that the graph goes from 0 to 2 pi. So really quick, if you haven't been graphing in polar mode, make sure that you change your graphing mode to polar. And then let's see, I'm going to use just that. Well, I'll retype them. And then I have to change my example a little bit. So 7 plus cosine theta, let's just take a peek at that. Oops, and there's a 6 in there. I tried to forget it last time I tried to make these too. Okay. And our graph, we're going to need to adjust the window a little bit here. So there are a couple options with your zoom, like zoom standard, zoom trig is one that I try a lot. This cardioid in particular is just kind of big. So 0 to 2 pi is appropriate. And then let's see, x, the negative was fine. It's just that we couldn't see the other end. So I'm going to go with 20. And then I'm going to make my y just a little bit bigger as well. I'm going to go -10 to 10 here. Okay, and now let's graph. Okay, that's a little bit better. So I mentioned in class how I like to trace a lot. That's what helped me get used to polar a little bit. So as we go through here, there's a couple I recognize. Like I think that last one was pi over, let's see, that'd be pi over 6. It makes sense. Remember that your graph is a rectangle, so it might not seem like the exact right angle. There's pi over 4, by the way. Pi over 2 makes sense on this one. Sometimes it's weird because it sends something backwards and it feels a little strange. What I'm just going to click through here now is get to the end of the cardioid. And it does end at 2 pi, 6.28. Now that's different in, I'm going to go ahead and graph part of the next one, which is, I'm actually going to change that to just a 6 cosine. So if you would change that for me, it's going to make our problem a little bit nicer. I tried to make notes for this one earlier and that turned out to be really gross, so I changed it. Okay, let's look at this graph. Okay, so let's trace again. This is one. By the way, I knew this should have been a circle on the x-axis because it was a cosine, and then the 6 means that the diameter is 6. The more interesting part that I wanted to point out is when you start and end, so we started at 0 and we go around, it ends at pi. Now I can keep going around here, but what that means is if I'm finding arc length, for instance, I don't want to go 0 to 2 pi because that would actually get me 2 circles all the way around, right? Same thing with area. When I'm finding area, I don't want to go 0 to 2 pi because that will actually go around that circle twice. Again, think about radar. It goes around that circle twice collecting area, which is not what I want. Okay, so let's look at example 2, and I changed the graph, but I forgot to change this. This one I want to be a 6, so pretend that's a 6 cosine theta, and that's what I have graphed here. And this first question is asking me where it intersects. So sometimes we can kind of eyeball it. I like to draw these in here, by the way. You'll see in a second. So I'm betting that's a pi over 3, but let's just make sure that that makes sense by doing some algebra. Okay, so those set equal to each other. And so 2 equals 4 cosine theta. So cosine is a half at pi over 3. And then if I think about all studs take calculus, the other spot where cosine is positive is down in that next quadrant. So in this case, they're wanting me to call it negative pi over 3. Now, if it's something that you're having a hard time solving, there is this solve feature. You cannot find the intersection in polar mode. So don't try to do that, or do try and just realize that for yourself. What you could do is you could actually go back to the XY mode and just pretend these are in XY for just a second, and then you could find the intersection in that particular mode. Just know that the graphs aren't going to look like those circly things like we have there. Okay, so on number 2, they want us to calculate the area inside of the circle but outside of the cardioid. Okay, so let's figure out where they're talking about. So inside this circle but outside the cardioid. So we can't really think top minus bottom here. We have to almost think like outer ring minus inner ring in this particular situation. So I can find the area of that circle, and there's a couple things I could do. I can go 1/2 and go integral from negative pi over 3 to pi over 3. Okay, that will give me the circle. I could also just do half. That's what I do a lot. So if I go 0 to pi over 3 and just double this whole thing, that's definitely something you can do. So you decide what you want to do there. The circle is that 6 cosine theta, so 1/2 r squared d theta. So that would give me, unfortunately, like all of this inside the circle. And what I'm hoping to do now is subtract out those little sectors there that are kind of the boundary is the cardioid. Okay, so we're going to subtract out in that same boundary. Again, you can just double that whole thing eventually if you want. So that's the, okay. And then on the calculator here, but I'm just going to leave it as set up. Okay, 3, the area inside the cardioid but outside the circle. So let's look at that again. Inside the cardioid but outside the circle. So they're like here and here. Okay, I'm going to put these little things in again because those can be helpful to see what's going to happen. Okay, so I think the problem is if I just do the cardioid, let's just say I'm going to do half of this because that makes sense to my brain, from pi over 3 to pi, and then I'll double everything. The problem is if I just try that, there's going to be this little sliver in here that I have to get rid of. Okay, so we have to think about Xing that out, and that part, the boundary, is the circle. Okay, so let's start to set that up. So I am going to just go pi over 3 to pi, and I'll just double this whole thing. And like I said, if I go do that and do under the cardioid, there's a little piece I'm going to have to take out. Again, that little tiny piece of pi, which actually the circle is the boundary, so I'll have to take that out. So I think that's the same boundary, it's just the circle this time. Okay, lots of drawing, lots of little sectors of circles, lots of questions, because sometimes, especially when there's 2 curves, the area can be a little bit challenging. So just let me know as we're going through, and I hope I get to do lots of examples with you on those particular ones.